All right, let's take a look at today's lesson. Today's lesson is on limits at infinity. We have several concepts that we're going to be going over, which are on this first slide. So let's jump in. First of all, let's look at some basic limits at infinity. This particular function we talked about yesterday or the day before, this 1 over x, if you recall, the graph of 1 over x, just a rational function. I believe yesterday we talked about what happens the limit as x approaches 0 from the right or the left of 1 over the x. Remember that? As it approaches 0 here, remember from the right it went to infinity, from the left it went to negative infinity. Now we're talking about approaching infinity, positive or negative infinity. And you can see from the graph as we approach an x value of infinity, our y value is getting closer and closer to 0. So it's going to tend to 0. Same way going the other way. If we're going this way to negative infinity, our y value tends to 0. So do you have to really commit this to memory? Well, if you know what the graph looks like, you'll be able to answer the question without having to memorize each little piece of it. So positive or negative infinity. This little guy right here, this is a fantastic limit. You're going to love this. It actually is let's kind of investigate it just a moment before I completely talk about it. So as we go to infinity, see the denominator grows without bounds, right? It gets bigger and bigger. What's going to happen to this fraction? It's going to tend to 0, isn't it? It's going to go to 0. So I'm left with 1 to infinity. 1 to infinity is not 1. Isn't that crazy? In this case, it's e. 1 to infinity is another indeterminate form that we're going to get to play with, but it's going to be a few weeks. So when we see it in this form, we're going to be, yes, this is just a formula. We can do the formula. We don't have to, though, if it's not in this form, we have to use some versions of L'Hopital, which we will get to in a couple of weeks. But right now, if it has a 1 here, which is the only kind you're going to see, right now, right, is with a 1. Has a 1 plus 1 over x to the x, that quantity, whether you're going to positive or negative infinity, is going to be e. And I'll show you how this can be adjusted on some problems on the next page. But this is a one that you just need to commit to memory. These two guys, the little arctangent guys, they actually just pop up all the time. You're thinking, oh, arctangent, we're just leaving them behind. No, I mean, we see them in like Unit 10. They're there. So let's talk about the graph of arctangent. Perhaps you already know. The graph of arctangent has 2 horizontal asymptotes, and it looks like this. Okay, it looks like that. So as the x values head to negative infinity, what happens is we approach the asymptote. This is the asymptote at x equals negative pi over 2, and this asymptote is at x equals pi over 2. So if we are headed to negative infinity, if the x values are headed to negative infinity, then our y value tends to negative pi over 2. If our x value is tending or heading to infinity, then our y value is headed to pi over 2. So those are 2 special limits that are pretty important for us. They kind of just pop up when you least expect it. So some pretty good limits. Any questions about those formats? All right. The next thing that we're going to look at are some definitions. This is on your formula chart. It's underneath the limit laws. So we are going to, they will be on a formula quiz, but they won't be on tomorrow's because, it's tomorrow. So let's talk about these definitions. These are calculus definitions of vertical and horizontal asymptotes. You have dealt with, from pre-cal and algebra 2, some like pre-cal kind of definitions of vertical and horizontal asymptotes. But let's look at what we talk about in calculus. So a vertical asymptote, the line x equals a is called a vertical to asymptote if and only if limit as x goes to a from the right is positive or negative infinity, or, so we only need one or the other, we don't need both, or the limit as x goes approaches a from the left is positive or negative infinity. So a vertical asymptote, that's like this, right? We know our little friend 1 over x has a vertical asymptote, and that's what it's talking about. So as we approach 0, the vertical asymptote is at 0. As we approach 0 from the right, in this particular case we head to infinity, so that would prove that there's a vertical asymptote there. That's just, you would be asked, find vertical asymptotes using the definition. That's what you would do. You would locate them and then do this limit. Horizontal asymptotes, very similar, just a little bit of a different twist to them, and that is, instead of headed to the location of the asymptote, we're headed to infinity, right? Because this one also has a horizontal asymptote, doesn't it? And so as we look at the limit as x goes to infinity, we're going to, if we have an answer to that, like if it's 0 in this case, then we have a horizontal asymptote there. That is the definition of a horizontal asymptote. One, or either or, one of those things would have to be true. Is it possible to have two different horizontal asymptotes? Yes. And we'll look at some instances where that is possible. Okay, so that is the definition of horizontal and vertical asymptotes. Are we okay with that? All right, the very last thing is, okay, something kind of cool. This has to do with infinity as well. So this is the limit of the ratios of two functions. It gives us some examples. So what we have going on here is like an ordering of how fast a function is, how fast it grows. This only works when we're going to infinity. I have had students try to use this before. In other instances, it does not work. It only works if the limit is going to infinity, which is why I have it under this category, limits at infinity. Now, so what does it do? Well, what we would have to determine is which one of the functions is the faster growing one. In this scenario, they're saying that f is the fastest growing one. So that means that if you have like x factorial versus like 2 to the x factorial is growing faster. So we have to determine which one. They call the faster growing one f. So if that's true, if the faster growing function is in the denominator, then that means that this limit will tend to 0. Right? That makes sense because the denominator is growing faster and faster and faster, so the fraction is getting smaller and smaller and smaller, and it's going to eventually tend to 0. If the faster one is in the numerator, then over time, as we head towards infinity, we're going to tend to infinity. Now these limits just work with the positive infinity. Okay, there would be differing things that would go along with negative infinities, which we can work with. So two of these little ones I kind of want to, we're not going to really deal with them in this class. I do want to talk about them just shortly. So this very slowest growing function is natural log. You know that poor little thing is so slow, right? Just barely kind of moves. So this is the slowest one. Then the next is polynomials. Polynomials are the next slowest. I'm really not going to be working with these two right here. So what does this mean? That means if I have a polynomial times a natural log, that's going to grow faster than the natural log by itself or the polynomial by itself. Right? That's all that means. And then if I were to, whatever these numbers were, the c and the d, if I were to take x, the c, and d, that would be even faster. But again, that's really minute things that we're not going to be dealing with. So I'm not even going to mess with those. We're just going to talk about the natural log, polynomials, a to the x, x factorial, and x to the x. Please understand that these are two different things. Okay, a to the x means 2 to the x or 5 to the x or 11 to the x. It's a number. It's not an x. This is truly an x to an x. Okay, and you can't beat that guy. That guy is the fastest growing one of all. Okay, and so we're going to look at some limits that we can solve this way by just really, and you're like, what? Just looking at it. We're just going to look at it and be able to tell. Too bad they're all not like that, right? They're not, but there are some that we can just look at and say if the answer is going to be 0 or infinity. Okay, we okay so far? All right, let's go to the examples on the second slide. I actually would like to start with this one first. This one is a more simple version of the first one. The first one is quite complex, so I want to go through a simple version of it before I get to that one on that very first one. All right, so you may or may not remember. Maybe you did this in pre-cal. I'm hoping you probably did. What is an algebraic way that we could solve this? We would multiply by 1 over the greatest power over 1 over the greatest power. So this is algebraically what we would do. Now, eventually, I would like for you to be able to just look at this limit and tell me what the answer is. Maybe some of you can do it right now, which is fine. But I'm going to take you through the process, the algebraic process, to prove that it is what, what we're thinking it is or what it's going to be. So I chose the largest power, which happened to be the first. So we take the limit as x goes to infinity. I'm going to multiply, so I have 3x over x plus 5 over x. So I'm distributing that 1 over x to each quantity in the numerator. I do the same to the denominator, so I get 6x over x minus 8 over x. All right, then I just pause a moment and see what I have. So this little fraction right here, hopefully you recognize as the denominator grows without bound, right? We're going to infinity. This fraction becomes smaller and smaller, and it tends to 0. What I normally do is I normally just put a circle around it, and that tells me that's 0. I don't need to worry about it anymore. Done with it. So I look, and that's why we do this algebraic technique, so that we can eliminate things and ignore them, right? So in the bottom, I hope you can see this one is going to go to 0. That's not going to be there any longer. Then we simplify what's left over. See, we have the x's go away, and my answer is 3/6, which is, 1/2. And in time, I would like for you to be able to just write the answer as 1/2. Just look at it and be able to tell. Which maybe we can. It doesn't matter. You can write the work or not, but that's what we're looking at. Are we okay with that? So now let's take this concept over to the more difficult one. Why is this one more difficult? It's because it has a radical. That just changes everything. And it's also 2 problems in one. They're kind of being sneaky with this here. Kind of throwing in an extra problem without maybe us realizing. It's going to plus or minus infinity. Those are going to be different. Okay, so let's talk about why. What's going on? When I multiply by, I need to multiply by 1 over the greatest. I need to talk to you about a concept that maybe you already understand. I'm just going to do a little scratch work over here. So the square root of x squared is actually equal to the absolute value of x. It is not equal to x. Let's talk about why. Some of your teachers may not have explained this to you. Maybe it wasn't really a point that they had to worry about. For half of all the numbers in the world, square root of x squared does equal x. But for the other half, it doesn't. So why? So what if x was negative 2? Okay, x is negative 2. Is that an equivalent expression? Yeah. What would happen if my absolute value bars weren't there? Would it be an equivalent expression? No. So to be truly precise and accurate, the square root of x squared equals absolute value of x. It's just a fact. Okay, so we're going to have to use that information when we're working with this because it's a mixed. See, it's partial square root and partial not. Right, so I'm going to have to multiply by something different here and here, but that are the same. So let's talk about that. So I'm going to multiply here by square root of 1 over x squared, and thereby 1 over absolute value of x. So I'll pause there for just a second and make sure we're okay. So we hopefully understand that the square root of x squared is equivalent to absolute value of x. See, that's still 1. I'm still multiplying by 1. These are equivalent. Now, I do want to talk about the absolute value of x. It is on your formula chart. It's kind of hidden up there with all the pre-calculus stuff. It's embedded in all that trig stuff. It's really important. There is a definition of absolute value of x that we should know. The absolute value of x is a piecewise function. It's x when x is greater than or equal to 0, and it's negative x when x is smaller than 0. That's the definition. So that causes a bit of a problem for us in this problem since we are doing both. We're going both to positive and negative infinity. What am I talking about? Well, if I'm going to positive infinity, I'm going to need to use this version of absolute value of x. Okay, this one right here, because that's good when I'm bigger than 0. If I'm going to negative infinity, I'm going to have to use this version of the absolute value of x. We cannot calculate with the absolute value. We have to translate it into a piecewise function. We have to take the absolute value bars off. I know you're going to be delighted to learn that every time you see an absolute value, think, oh, I get to do 2 problems, right? So if you have absolute value derivative, you get to do 2. See, this is great. So absolute value, you're thinking, yes, I get to do twice the work. All right, so we just need to know this definition when we move into this problem. So I'm going to do the first one, going to infinity. I'm going to go ahead and multiply everything out so that it's very clear what we're doing. X squared times 1 over x squared is 1. 2 over x squared. Okay, so I'm hoping the numerator is fine for us. The denominator, we have 3x over absolute value of x minus 6 over absolute value of x. Okay, so I'm just going to actually leave this to be the plus and minus. Let's just leave that as the plus and minus. That's our standard one. We're going to take that and run in both directions. So this is just limit as x goes to plus or minus infinity. We're still good. We have absolute values. Let's look at the case where it's the limit as x goes to just positive infinity. The numerator is going to be the same. The denominator, since we're going to positive infinity, these absolute value x's are just an x. So at any rate, these two are going to go to 0. Right? Those are going to go to 0. So really it's this one that I'm concerned with. This is just an x. So it would be 3x over x minus 6 over x. We know those go to 0. That goes away, and our answer is 1/3. Okay, so that is the answer if we're going to positive infinity. What if we're going to negative infinity? Let's reference this again up here. So the top numerator is the same. Denominator. So this time I'm going to negative infinity. I have to use this version of the absolute value definition, the negative x. So I have to say 3x over negative x minus 6 over negative x. Those are still going to 0. Those x's still cancel out. But my answer now is negative 1/3. All because of the radical. Yes? I would say 95% of the times it's plus or minus the same number. I have seen instances where it is not, so I would be cautious. Yeah, 95% of the time it is plus or minus that same number. But of course, I could certainly come up with one where it wasn't. That would be fun. Okay, are we okay with that? Those two, yes ma'am. You have 2 answers to that. When we're going to positive infinity, it's 1/3. Negative infinity, it's negative 1/3. Okay, and I've even seen it where they've been reversed. So, are we okay? All right, so let's see. Let's look at this. Let me erase. Everybody have what they need over here? Okay. So let's go down to this example number 4. Now this is one where we're thinking, oh my goodness, 2 to the x factorial? I can't think of any algebra stuff to do to that. So that's when we think, oh, rates of growth. Maybe that will work here. So let's look. So we have the function 2 to the x, also known as a to the x, right? Please don't get this confused with x to the x. This is a to the x over something with x factorial. We need to think to ourselves which one is the fastest growing one. So we would have that, sequence in our head. We would know which one is faster. X factorial is faster. When the denominator function grows faster, then the whole thing tends to 0. So basically you just look at it and you say it tends to 0. We okay? So we kind of like those, right? That's not bad. Just figure out which one's faster and there you go. All right, I'm going to skip to this last limit one and then I'll go to the vertical asymptote one. If we're doing the limit as for sine, I would just encourage you to think about what the graph of sine looks like. The graph of sine, it just goes on forever like that, oscillating. So as the x value is headed to infinity, do we have a particular y value that we're headed to? No, I mean it's just bouncing back and forth, isn't it? So this is a D and E. And the reason, because you are typically asked why. Why is it a D and E? It's because of oscillating behavior. Or you can just say oscillating. It's oscillating. That's why it's a D and E. Okay. Last problem. We're being asked to find vertical asymptotes using the definition. Okay, the vertical asymptotes. We haven't been told what A is. You know, some problems they'll tell you what A is and they'll say, show that A equals, you know, whatever is a vertical asymptote. We don't know what A is. So we have to use our pre-cal algebra 2 knowledge to figure out what numeric value would cause the denominator to be 0. Because that's when we get vertical asymptotes, right? It's when the denominator is 0. And that would be a plus or minus 1. Right? So A is a plus or minus 1. That's what A is. So now I have two numbers to prove that they're vertical asymptotes. So we have to know what the definition of vertical asymptote is. If you recall, we have to do a limit. It doesn't matter which side you go to. Of course, I don't know why I picked the left side. So we do the limit as x goes to 1 from the left. I'm going to check out the 1 first. And I'm going to call this f of x. I encourage you to do this kind of thing so that you can just say the limit of f of x. Why? Because you can do that on the AP test and it saves you time. So yes, you just call it f of x, g of x, whatever you want to call it something. So then when I rewrite it, I only have to say the name. All right, so let's think about this for a second. Let's use the technique that I taught you, I think it was yesterday. It's numeric. We want to think numerically. If I am going to 1 from the left, I'm going to think 0.9. I always go a tenth. 0.9. If I put a 0.9 in the numerator, I'm going to get a positive number. If I put a 0.9 in the denominator, I'm going to get a negative number. That means I'm going to negative infinity. Remember we talked about that technique. Because why? Because this is a vertical asymptote. If you graph this, you would have a vertical asymptote at 1 and negative 1. And how, you know, and the definition says the right or the left. You don't have to do both. So I did the left, check. It's a vertical asymptote. I use the definition. Let's check the other one out. The limit as x goes to 1 from negative 1 from the left of f of x. Okay, so negative 1 from the left. So we would use like a negative 1.1. All right, negative 1.1. We would do that number, kind of calculate that in our head. What happens if we put a negative 1.1 in there? So negative 1.1 times negative 1.1 versus 2 times negative 1.1. You hopefully will see we are going to have negative at the top, positive at the bottom. So this is also going to negative infinity. Okay? And so therefore, the vertical asymptotes are x equals 1 and x equals negative 1. And we've proved it using the definition. All right. How is that? We okay? Mm-hmm. Which one? Oh, thank you. Oh, I love this one. I almost forgot about it. That would be terrible. That's a great one. And you need to know about it, right? Yeah, you need to know about it or you're going to be at a disadvantage. I don't want you at a disadvantage. All right, so let's fix that. And it's actually pretty easy. Yes. This one? This one? If it says, oh, this part or this part? So let me explain what you have to do. If it says using the definition, you have to use the definition. You have to do this part. If it just says, and it's calculus, so it's not going to just say find vertical asymptotes because that's not calculus, right? That's like pre-cal. It's going to ask you to use the calculus definition, so you would have to do this part. Okay? Now this one, this is our little friend right here. This is a fantastic thing for us because we can just look at it and tell the answer. We can just look at it. Unlike the ones that I'm going to give you in a few weeks where you have to use L'Hopital's, which are super fun. Okay. So let's look. What's different from this than the original function? I have a 2 in the denominator, right? That's different. So I'm going to think about this as a fraction though. Because my answer is e to the 1/2. That's my answer. Okay, so let's talk about that. So if I have a number in the denominator here, now this is always going to be a 1 for us right now. I'm not going to give you any that you have to use L'Hopital on. So if I put a 4 here, it's going to be e to the 1/4. All right, we see the pattern? Okay, this is a great pattern. If you don't like the pattern, you can do it the long way, and I will show you in a couple of weeks. But until then, we're just going to use the formula. So let's say instead of a 2 there, let's say I have that same limit and it's 1 plus, oh, let's say it's 3 over x to the x. What do you think that answer is going to be? It's going to be e cubed, right? E cubed. Okay? What if it's 1 over 3 halves x? 3 over 2x. It's going to be e to the 3 halves. We have that straight. But there's more. Also, there could be a number here, up here with the x. So what if you had, same limit, 1 plus, we'll keep it simple, 1 over x to the 4x. Our answer is going to be e to the 4th. What if you think that said 1/4 x? It'd be e to the 1/4. And even fancier and more fantastic, what if there are numbers in both places? You would multiply them. Exactly, you would multiply them, that's all. So let's just, again, we'll just make an example. What if we had 1 plus, 2 over x times 1/3 x? So our answer is going to be e to the 2/3. Okay? I'm hoping that's okay. Right? So we love the formula, right? When you see this, you're going to be like, yes! I just have to look at it and write the answer down. It's going to be easy. Okay? Mm-hmm. This one, because the definition says or, left or right, you don't have to do both. I mean, you can if you want. Yes. Yes. Because they don't have the same quantity underneath, they're not going to cancel, right? When you have radicals and you multiply radicals, you're multiplying the things underneath, and they don't, like, cancel out, so it stays. Okay? Are we okay?